All right, so what I'm going to do now is to share my screen. All right, so I don't know, Wyndham, did you get the video? Did you go through it? Are we there?
Yes, I went through it.
All right, so do you have questions that you want to ask?
Um, Not really. No, I don't.
Okay, so please,
But
I think
I want you to dwell while you explain. I want you to dwell more on the neutron um density law.
okay, all right. So the please, you have to make sure that your Zoom is having your name. Who is using this Techno Pop 4 Air? Who is using Technophone? Someone just came in with Technophone. You have to make sure that your name is there so that I know exactly who is entering. Who is with Technopop? It's like the person's network is even disturbing. All right, so Naomi, do you have any area that you want us to touch? Naomi, do you have any particular area that you want us to touch? She's not on. All right. So I'm going to basically, most of these things have been explained in the video. Basically, most of them have been explained, well explained there. So I'm going to take us to the key area, key thing that I want us to explain. All right. So this is basically what we are going to have. This is basically what we are going to have. So what we are going to do most of the time is, I'm assuming that we all understand what well is. But if I have to refresh our mind, I will take us back. I will take us back to the first page. If I have to refresh our mind, I will take us back maybe to the first page. All right. Once a well has been drilled, we know that drilling a well means that probably they must have seen enough sign that there is hydrocarbon within the subsurface. So once the well has been drilled, they need to go further to investigate the subsurface to see if there is actually enough hydrocarbon and if the properties of the rocks are sufficient enough for the hydrocarbon to easily flow. Because at times they may drill what we call a wildcat well, which is just a well probably to investigate that particular area. They may not have confirmed with 100% certainty that there's hydrocarbon there. They may have seen from surface survey, from seismic, that there are evidence of hydrocarbon there, but they may want to see enough proof to show that there's evidence of hydrocarbon. So what they will do now is they're going to drill a well. Once the well has been drilled, they have now to send sensors. These are sensors that are sent inside the well. Once the sensors are sent inside the well, the vehicles that we see at the surface now will start pulling the sensors out of the well. The measurements are made when the sensors are being pulled out of the well, not when the sensors is being sent inside the well. Generally, they must have defined the speed of the vehicle at the beginning of the experiment. They must have said, okay, we expect this vehicle to move at this speed so that the sensor can measure properties at this interval and this interval and this interval. The properties that the sensors are measuring are physical properties of the rock. That's why we call it petrophysics. They are measuring physical properties of the rock. So we have physics and rock coming in. So once the sensors have been pulled, once the sensor is being pulled out of the well, It now takes measurement at regular interval. This interval could be 0.5 meters, it could be 0.5 feet, depending on whatever unit they are using to carry out the measurement. So once the sensor is being put out of the well, it can measure so many properties. Those properties could be natural properties of the rock, or it could be induced properties of the rock. There are times that they need to send in signal into the well, and then the well now will generate some kind of information that tells us something about the physical properties of the rock. There are others that would measure the natural property of the rock. That means they don't need any device that is going to send it. They don't need a source. Let me put it that way. They don't need a source. So there are two ways in which the measurement can be made. We have measuring, we have measurement, natural measurement, and then we have artificial measurement. For this artificial measurement, we will have a situation where there is a source that first of all sends in signal. This signal now generates some kind of property that the receiver now has to measure in order to determine the physical property of the rock. So if we are talking about natural properties, which we are going to see. So this was just a brief of what well log is all about for someone who have never heard about well log. Now, if we look at these properties, if we look at a typical outlier of a well log, what we have here. All right, if you look at this is a typical layout of a well log after the measurement must have been made. After the measurement must have been made, they now have to display whatever have been measured in order to do a good interpretation of it. So they'll generally represent this log in three tracks. We have this track, which is the lithology track. We have the resistivity track. In this case, they have put the resistivity at the tail end, but most of the time you may have it at the middle of it. So we have the resistivity track, and most of the time will be at the center. And then we have the porosity track. We have the porosity track. Now, for this lithology track, what will you see there? You will see gamma ray. You may see gamma ray. You may see caliper. You may see spontaneous potential. Spontaneous potential. These are different types of logs that probably you must have studied in class, but we are not going to go and touch all of them. We are not going to go and touch all of them. Now, for a gamma ray, like I've already explained, this sensor can measure properties naturally without any source, and it has to measure property with a source present. So gamma ray now measures what we call natural phenomenon. You don't need any source to generate anything before you measure it. It just simply measures the natural radioactivity of elements that are found within that particular rock. These natural radioactive elements could be thorium, it could be uranium, and it could be potassium. It could be thorium, uranium, and potassium. So what we have to do now is differentiate the content of these various radioactive elements in the various rock types that we have, so that when we see a particular trend, we may easily know if it is shale, if it is sandstone, if it is carbonate, dolomite, also, and so on and so forth. So generally, what we have to do is to differentiate between reservoir rocks and non-reservoir rocks. Reservoir rocks generally are rocks like sandstone and carbonates, mostly around the Red Red Basin and the Niger Delta Basin. We have the sandstone there as the reservoir rock, but we have carbonate rocks also as reservoir rocks in the Middle East and also in the Gulf of Mexico. We have sandstone there that occur as reservoir rocks. So basically, we have two types of reservoir rocks. We have sandstone and we have limestone. And generally, our source rock will be shale, but we have instances where the source rock is also limestone. So it's possible for limestone to act as a source rock and also as a reservoir rock. So how do you use the gamma ray now to differentiate between these two types of rocks, the reservoir rocks and the non-reservoir rocks? Generally, if we have shale, which is a non-reservoir rock, it has a high content of uranium because uranium is mostly found in organic matter. So we expect that shale that contains a lot of organic matter because our hydrocarbon is generated inside the shale. So since shale contains a lot of organic matter, we expect that shale is going to have a very high uranium. And if shale has a very high uranium, therefore we expect that the reading of shale is supposed to be high. The reading of gamma ray is supposed to be high in a shale interval. It's supposed to be high in a shale interval. I don't know, Wyndham, can you get me? Or is the network fluctuating? Wyndham, are you getting me?
I can hear you.
All right, all right.
I can hear you.
All right, okay, good enough, good enough. All right, so we expect that for shale beds, we expect to have high gamma ray value because of high uranium. When it comes to thorium and potassium, you may not really differentiate between reservoir and non-reservoir rocks when it comes to uranium, to thorium and potassium, because shale, for example, will contain clay minerals, and these clay minerals may have thorium and they may have potassium. Sandstone, for example, will contain feldspars, and these feldspars, this sandstone may contain feldspars or K feldspars, and these K feldspars have a lot of potassium in them. So when it comes to potassium and thorium, you may not really differentiate it that much from source rock, from reservoir rock, and the non-reservoir rock. But uranium gives us a clear distinction. For a source, for a reservoir rock, it is very, very low, and for a non-reservoir rock, it is very, very high. That's why you come here and you see a very high reading. If you look at the scale, it's from 0 to 150. We have a very high reading here. So this will tell us that this is a non-reservoir rock. Then when you come here, you see a very low reading, and then this will tell us that it is a reservoir rock, which could be basically sandstone or limestone. But here we have a very high reading also that is telling us that it is a non-reservoir rock, which is basically our shale. Now, if you go now to the resistivity track, I would like to take it in that manner. You go to the resistivity track, you now realize that first thing, we go now to our basic physics or chemistry, and we define what resistivity is all about. Here we are talking of resistance to the flow of current. Resistance to the flow of current. That means if we have a material where current can easily flow through it, it has a very low resistance because it doesn't stop current from flowing. Resistance means that it's a material that stops current from flowing. So if you have something like water, current can easily flow in water. So we expect that the resistance of water is going to be very, very low. So when we talk of resistance, we are talking of resisting the flow of electric current. That means it's trying to stop or to block the flow of electric current. But if electric current can easily flow through you, then you have a very low resistance. You have a very low capacity to block that flow of current. But generally, when we come to hydrocarbon, it has a very, very high resistance. Hydrocarbon has a very high resistance. So once you now go to the reservoir zone, the next aspect now would be to differentiate if this reservoir has, if it has a hydrocarbon or it has water. Because the fact that it is a reservoir does not necessarily mean that there must be hydrocarbon there. You might still have a reservoir that has nothing, which is useless. So we have to go now to the resistivity track in order to look at the reservoir to see if that reservoir actually contains hydrocarbon or it contains water. If you look at what we have here, you realize that since hydrocarbon, they have a very high resistance, and we have a high resistance here, then it means that this upper part of that reservoir contains hydrocarbon, and the lower part, we can actually see that at the lower part, there is low resistance, which means that we definitely have water at the lower section. And this is going to confirm the segregation that we have within a reservoir, because within a reservoir we may have different fluids. these fluids now will be segregated according to their density. So we expect that water which is denser than oil and gas, it will settle at the bottom. While oil, which is higher, which is the less dense than water, will settle above it. Then gas, which is much more less dense than all of them, will settle above all of it. So we can actually see that above this layer where we have the low resistivity, there is hydrocarbon there. But if I look at the resistivity, I may not be able to differentiate between oil and gas. I may not be able to differentiate between oil and gas. So what it will tell us if that reservoir contains oil or gas will not be the resistivity tract or the lithology tract, but it will be the porosity tract. The porosity tract now will tell us whether it contains oil or it contains gas. So that's what the resistivity tract will definitely tell us. Now, if I go now to the last tract, which is the porosity tract, the porosity tract. Now, I will look at the porosity tract and see what I have there. I have the neutron log and I have the density log. Now, first thing first is the density log. The density log is also called the gamma ray log. This one is the gamma ray log. This one is the gamma ray log. Well, that measures what? The natural gamma ray within the formation that is emitted by what? Elements, that radioactive elements that are found in the formation. Radioactive elements that are found within the formation. But if you come here, the density log is the gamma ray log. So what does the density log measure? There is a source that is present. So for density and neutron log, we need a source. For the resistivity, please shut down your mic. Please, the mic, the noise coming down from the mic. Gamsi, shut down your mic.
Okay, sorry.
All right, sorry about that. We continue from there. So I said the density log is the gamma ray log. That means what happens is there is a source that emits gamma ray. There's a source that emits gamma ray. This gamma ray travels within the formation. It travels within the formation, collides with particles within the formation. Then this gamma ray is deflected to the source. There's a receiver there that receives the amount of gamma ray that has been deflected by particles that are found within the particular formation. That means if we have particles that are very dense, it means that these particles, if you have a formation that is very dense, it means that the particles within the formation are very close together. They are very close, packed together. In that particular case, there will be no space between them for gamma ray to travel through. So in that particular case, what will happen is that more gamma ray will be deflected to the receiver. So if you have a denser formation, more gamma ray is deflected to the receiver. But if you have a less dense formation, it means that it is actually porous. And if it is actually porous, it means that some of the gamma ray could easily pass through these pore spaces undeflected. That's why when we have a very dense formation, the gamma ray reading is, the density log is high. The density log being high simply means that more gamma ray have been deflected to the receiver. So if we look at what we have here, the density log is actually, I think this is the kind of blue in color. The density log is actually, this is the density log that is actually there. You realize that generally the non-reservoir rock, which is generally our shale, will be more dense than our sandstone because this reservoir rock contains fluid, and it contains fluid means that it is porous. So this particular formation would definitely have high density. That's the density there that is high. When it gets now into the reservoir zone, the density now drops. The density now drops. Why? Because our reservoir rocks generally are porous. It means that some gamma rays will actually go through it undeflected. So the density drops, and it drops drastically in this interval because we expect to have gas in that particular area. So the density also depends on the type of fluid that is found within that reservoir. We know that gas is very less dense. So we expect that because we have gas in that particular formation, the density log also is going to be very, very low. If you look at the scale here, it's from 2 to 3. So it is increasing in this direction. It's increasing in this direction. So the density log is low here. When it now gets into the oil zone and the water zone, the density now increases because the density of oil and water, they are greater than that of what of gas. But we cannot really differentiate that much between oil and water density, even though water is more dense than the oil, but the difference is not that much as compared to gas. Gas is very, very light. Now, when you get now, let's look at, now we have explained the density log. Let's look at now the neutron log. Now, with the neutron log, there is also a source that is present. This source, what does this source do? The source emits high energy neutron into the formation. You remember that when it comes to the density log, it was emitting gamma particle. It emits gamma particle, the particles are deflected to the receiver. But for a neutron log, this source emits neutron particle, high energy particle. This high energy particle, they call it the epithermal neutron.
Thank you.
Please, Akone, please, your mic is on. Can you shut it, please?
Not of my audio for here.
Hey, that's black.
All right, let's move on. So when the neutron log emits high energy neutron, which are called epithermal neutron. When it emits this high energy neutron, the neutron travels within the formation and collides with particles. We all know that once a material collides with another material, there must be transfer of energy. There must be energy that is lost in the form of heat and so other types of energy. If there is sound or possible whatsoever, we may have some other types of energy that is converted to. So when this neutron collides with particle, it slows down because it transfers some of its energy to these particles that it collides with. So when the energy collides, it slows down to a level where we might now call it the thermal neutron. The energy has reduced to a certain level, which we might call it the thermal neutron. At that particular stage, the neutron is still moving. The energy may have slowed down, but it is not sufficient enough for neighboring atom to capture the neutron because the energy is so high in such a way that neighboring atom cannot capture the neutron. So when it slows down at that level, we call it thermal neutron. It may collide again to a certain point where it slows down drastically to a point where the neighboring atom now may capture the neutron. When neighboring atom captures the neutron, in that process, what gamma particles are also released. So we have different processes that are taking place. We have thermal neutron that is produced. The energy slows down to a point where the neutron is captured. At the point where the neutron is captured, alpha particles are released. So a company may design their instrument in such a way that it determines the amount of thermal neutron that is available within the formation, or it detects the amount of gamma ray that is emitted as a result of the neutron being captured. So those are the two principal ways in which company may design their instrument. Different companies, Schlumberger may design in a different way, and other company may design in a different manner. Some may design it to measure the amount of thermal neutron. Others may design it to measure the amount of gamma particles or alpha particles Alpha particle may emit alpha particles also that are emitted as a result of that neutron being captured. So now, how do we use the neutron now to differentiate between the various properties within the formation? The problem now is the rate at which it slows down. When it collides with other particles, it slows down. But it slows down more when it collides with a particle that has a similar mass to it. When it collides with a particle that has a similar mass to it. And within the formation, hydrogen is the particle that has a similar mass to neutron. So when it collides with neutron, it slows down. When it collides with hydrogen, it slows down faster than when it collides with any other particles within the formation. So generally, for a neutron lock, we are going to refer to it as the hydrogen index lock. That's why they usually call it the neutron hydrogen index, because it determines the amount of hydrogen that we have within that particular formation. Now, if we look at basically our chemistry at the lower levels or probably at secondary school, you realize that from when we talk of the organic chemistry, you realize that within the formation, gas that probably from methane, C1 to about C3, C4, C1 to about C4, then from C5 to about C15, they are liquids, and then from C16 upward, they are solids. So you realize that gas have the lowest amount of hydrogen, followed by liquids before solids. So if we have to determine the amount of hydrogen within the fluids that are found within the reservoir, you realize that gas has the lowest amount of hydrogen, then followed by liquid. So we expect that if this is our neutron log, the first thing is for you to identify the direction of increase. This is the direction of increase. We have negative 18 here, and then we have 42 here. So we are increasing in this direction. So you realize that once you get into the reservoir rock, what happened is that there is a drastic decrease in the neutron log reading. This drastic decrease in the neutron log reading tells us that we have a gas around this area that has a low amount of hydrogen, because we have said the slowing down depends on the amount of hydrogen within the formation. By the time it gets to a zone where we may have oil that has a higher amount of hydrogen, you realize that there is an increase. There's an increase in that value. So generally, for you to plot this porosity track, you must always crisscross it. That means density is increasing in one direction and neutron is increasing in the opposite direction. Otherwise, you will not have this effect, this bulge in here, which we call the balloon effect or the gas effect. Once you have this bulge in here, it is sufficient enough to tell you that what we have there is a gas, not oil. What we have there is gas, not oil. You may have already differentiated between oil and water using the resistivity track. We have already differentiated because we know for a sure that we have hydrocarbon within this interval. Since we have this bulging around here due to drastic drop in density and drastic drop in neutron value, it simply tells us that we have a gas around this area. In this area where there is no large separation between the neutron and the density, we have oil there. We don't need to go down here because we already know for sure that what we have here is water from the resistivity track. So we will use the neutron density cross plot in order to differentiate within this hydrocarbon zone what is oil and what is gas. So basically what I have explained here is what we call qualitative analysis, because there are two types of analysis that we are going to do. Tomorrow we'll do qualitative analysis using TEDLOG. Then the day after, we are going to do quantitative analysis. That means we are doing calculation. I don't want to go and talk more about all of the formulas that we are going to use, because we are going to see these formulas inside the software. So you can go through the video again if you want to have a clue of this. So this is basically what I have taken time out to explain. First thing is to differentiate between reservoir and non-reservoir rock. We use the lithology track, which is basically we may use gamma ray to differentiate between what is reservoir and what is non-reservoir. Once we get to the reservoir, we have to differentiate between hydrocarbon and water using the resistivity track. And then from the hydrocarbon, we have to differentiate between what is gas and what is oil using the neutron density cross plot. I will not talk more about the quantitative analysis because it's basically using formulas to calculate porosity, water saturation, and permeability and all of that. Those formulas are inside the software. Once we get to the software, we are going to see how we can easily get these formulas. We are going to see how we can easily get some of these formula. So this is just a review of what we have inside that the recording that I sent. So if you have any difficulty, you might just ask. Widum, any difficulty that you want to clarify? If not, then we'll end here for today, and tomorrow we go straight to the practical section. Today was just supposed to be a review. So any difficulty?
No.
Okay. So your doubts have been clarified, right?
Yes, it has. Thank you.
Okay, I hope it was a good section.
Yes, it was.
All right, all right. So it was just this class of today was just to probably give us a review of this.